Yes, class, this is the video for section 7.3 as I promised. Okay, in this section, we're talking about repeating decimals. And you want to know why repeating decimals occur and how to tell if a decimal will repeat or not, how a fraction can be converted to a repeating decimal and then vice versa, and then ordering of repeating decimals efficiently. Okay. Now, from the 7th grade, students should be able to convert a rational number to a decimal using long division. Okay. Know that the decimal form of a rational number terminates in zeros or eventually repeats. And so from these examples, I want us to know and be able to tell why does the pattern in each of them repeats. Why does the pattern in each repeat? Okay. Now let's look at the first example. Now notice that the rational number here is 1 over what? Over 7. In this case, is what? 2 divided by 13. And over here you have 5 divided by what? 18. Okay. Now how do we know whether this terminates or not? If you use the previous section in section 7.1, using the theorem 7.1, you 18 in the it's 9 times 2, so you have 2 times 3 squared. And because the prime factorization of that has what? A 3 in it, all right, it doesn't terminate. Okay, 13 is a prime number, so it is not 2 or 5, so it doesn't terminate, as well as what? 7. So from the section 7.1, we know these rational numbers will not terminate. So let's use the long division. I will just do one of them, and then I will ask, how could you tell that a pattern repeats? Okay, 7 into 1 is not, so you put 0 and then a decimal, all right? And then if you multiply, you added 1 to that, so that becomes a 10. 7 into 10 is 1. 1 times 7 is 7. If you stop trying to get 3, drop down to 1, 0, or add 0 to that. 7 to that is 4. 4 times is 28. If you subtract, okay, you have, so you're going to subtract, this will be, just try to get, you get 2, add 0 to that, that is what? That is 2, that's 14. If you then subtract, you get 6, add 0, you get 8. 8 times 7 is 56. Subtract, you get 4. You add 0. You get what? You get 40. 7 into 40 is what? 5. That's what we had, a 5. And then we get 5 times 7 is 35. Subtract, you get 5. And then bring that, add another 0. 7, that's 49. That's 7. 49 is to get 1. Now, why does this a pattern 1, 4, 2, 8, 5, 7 repeats? Why does it repeat? It's because we started with 1, and then we are ending with 1. So right after this, we're gonna have 1, 4, 2, 8, 5, 7. It's gonna go like that. So that is why the pattern here, this pattern we see here, it repeats, because the one that we started with, that is the remainder right now. Okay. Similarly in B, okay, we started off with a dividend of 2. And then at the end, we're going to start the remainder. Once you get 2, then this pattern is going to what? Is going to repeat. You get the next will be of 1, 5, 3, 8, 4, what? 4, 6. Okay. Now, this one you don't get a 5, but look at what is happening. 18 into 50. Okay. It is 2. So that's 36. If you stop trying to get 14, add 0 to that, you get 140. And then 18 into 140, that is what? 7 times, which is 126. If you subtract, you get what? So the 14, this one repeats. Okay. Here, the 2 repeats. Over here, the one that we started off with repeats. Okay, not the difference. The two we started with, okay, we're gonna repeat. The one we started with is repeating. Over here, you don't start with a 5, but they will see that each time you're getting 14, and so because 18 doesn't go into, you're going to add 0, keeps adding zeros, making it 140, and so this pattern here is going to repeat. So that's the reason why this is going to be 27, 27, 27, and so on and so forth. So in each of these, we're going to write this as you have 1 over 7. It is 0.142857, and we put what, a bar on top, meaning that it is repeating. The second one, where you have 2/13, it is 0.153846. All this is going to repeat. And then for the last but not the least, you get 0.27 repeating, which is equal to the 5 over 18. Okay. All right. Now let's go to the next page. So let's define what is the part that is repeating has a special name. So the repeating block of the digits, all right, is called repeatant. And the period is the number of the digits that repeats. Okay, so as you can see, for A, the repeatant is the 154. This is the repeatant. Now, how many digits in the repeatant? So the period is what, 3, because there are what, three digits, 154 in the repeatant. Okay, now second, what is the repeatant here? The repeatant is what? The 54. The 54 that is repeating. Now what's the period? The period is what? Is 2, because there are 2 digits in the repeatant. The first one, there are 3, so the period is what? Is 3. Okay, so let's have a question. How many digits does a repeatant have? How many digits? Okay, how many digits does a repeatant have? For example, if I have the 1 over 7 that we did, okay, I could use the long division, but let's use the calculator to find those. Okay, so 1 divided by 7. Oh, my computer is currently not on. Let's clear that. 1 divided by 7 is what? 1.142857. 1.2857. Okay, so how many of the in other words, what would be the period? What is the period given any rational number? Okay, so do you know that this is what 0.142857? That's what that repeats. How many are they? 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Now the question is that how many reminders? Okay, how many reminders before the pattern begins to repeat? So let's go here. How many reminders? Okay, there is 1 here. Okay, there's another 2. That's a remainder. There's another 1. There's a 4. There is what? 5. Okay, and then before it starts repeating, so 1, 2, 3, 4, 5, 6. How many was the period? That is 6 digits in the repeatant. Okay, over here, talking about the remainder, how many? There is a remainder of 7, 1 here, 5, remainder of 5, remainder of 11, remainder of 6, remainder of 8, and then a 2. 1, 2, 3, 4, 5, 6. Okay, how many remainders are there? Because there are 6 remainders, that is why the period is what? It is what? 6. In other words, the repeatant has a block of 6 digits. Okay, the pattern has a block of 6 digits, or the repeating number has a block of 6 digits. All right, good. Now, so the answer to the question is that in general, if I'm given any rational number 1a over b, okay, in its simplest form, and then b is not equal to 0, and b is greater than what? Is greater than a, just like 1/7. Okay, the 2/13 that we did, that the number, let's write them here. This is 0.153, 153.846. This is repeating, and over here you have 0.27 also repeating. Okay, so 7, you have 6 blocks, 6 digits in the block. 13, you have 6, and then 18, you have what? You have 2. So the question is again, what is the period, and then why? How many digits does what a rational number, a repeating rational number will have? Okay, the answer is that in general, when you have, again, when a over b is a rational number, then b is not 0, and b is greater than a, and does not terminate, then a repeatant has at least b minus a digits. In other words, the period is what? B minus what? A. Okay, so the 1, see the 7, the repeatant, the period in this case is what? 7. To have at most 7 minus 1, so to have at most 6 what? 6 digits in the what? In the block. 18 minus 1 is what? 17. So it means it will have at most, please, it's not, it didn't say that it's equal to 17, but at most 17 what? Digits in the repeatant possible. Okay, now here is an application. It says you want to write 1/9 as a decimal. Okay, use your results to mentally compute the decimal representation for each of the following. Okay, so what is 1/9? 1/9 as a decimal, if you use a calculator, 1 divided by 9, 1 divided by 9, you can notice that it's what? 0.111111. So this is 0.1, okay, 0.1, or this is what? 0.11111, keep going like that. So if you have 2/9, it said use the word mental computation. How do you write it? I know 2/9, this is the same as 2 times 1/9. You see where I'm going with this one? 2 times 1/9. Okay, and so this is 2 times, and then 0.11111. So this is what? 0.2222, 2 times that, or in other words, 2.222, keeps going like that. Similarly, 3/9, we can write that 1/3, but we want to use this result to be able to write a repeating decimal for that. So that is written as 3 times 1/9, and that is equal to 3 times 0.111111, okay, which is equal to 0.333333. Similarly, this is equal to 8 times 1/9, and that is 0.11111 times what? Times 8, and that gives me 0.888888. Keeps going, so that's 0.08 repeating like that. Okay, all right. Now another example is a find the decimal expansion of the following, and then guess the decimal expansion of 1 divided by 11111. Explain your reasoning. Okay. So the solution, what is 1/11? Let's use a calculator to do that, to be easy. That's why sometimes calculator comes in. 1 divided by 11, okay, it is 0.090909, so which is equal to 0.09, okay, repeating. Now, what is 1/111? When you have divided by 3 ones there, what is that? Decimal. Okay, 1 divided by 111. It is what? 0.009009. So this is 0.009009. Keeps going, and that becomes 0. It is equal to 0.009 repeating. And also 1 over 111, that's 4. What do you think that will be? Okay, can you guess? All right, now you have 2, you get 1 0 and then 9. You have 3 that are ones in the bottom, 2 zeros and then 9. So this would be 0.000 because there are 4 and then 9. 0.000 and 9. So you're going to repeat like that. Let's use the calculator to check. So you get the 1 divided by 111. Okay, 0.0009, 0009, 0009 in that order. So you guess this was 0.009. Actually, 3 of them. Okay. Point zero zero. Okay. All right. So now, what can you guess? 1 over 11111. And what would be the reason? 0. What? Now the reason is this. Okay. If you have 1 divided by 11, that's 2 the ones in the denominator. There is 1 0 and a 9. You have 3, you get 2 zeros and a 9. If you have 4, you will be 4 zeros, 3 zeros, and that is the number of ones in the denominator minus 1. That gives you the number of zeros that comes before the 9 after the decimal point. And so if I have this, what is 5 minus 1 is 4. So I get 4 zeros, okay, and then the 9. And that's what's going to repeat. Okay. So the number of zeros before 9 after the decimal point is equal to the number of digits of the denominator minus 1. Okay, so that's a reasoning. And then finally, if I have a rational number, how do I convert it to a fraction? Sorry, if I have a repeating decimal, how do I write in the form of a fraction? So we are converting a repeating decimal to a fraction. Okay, repeating decimal to the form a over b. Okay, now this week your discussion is about, if you look at that article that I posted, it deals with this. All right, so how do we determine some of this? Now, first example, I pick these examples, intentionally. Okay, now if you have the repeatant occurs right after the decimal point. Okay, this is how we approach it. First, the algorithm, you let n or x equal to your number which is given. Now the reason is that if you want to, this is repeating, if you want to solve this, this is not equal to, see, 0.26 is not equal to 0.2626 because this keeps going. So first, what you do is that you write it, you let that rational number be n. Okay, so n is your rational number. It's of the form a over b. Then you want to, because the repeatant is the period is 2. Okay, the period is 2. So you multiply by 100. So you get 100n is equal to, if you multiply this by 100, it will be 26 0.262626. So that is that. And then you subtract. The next step is that, let's write it here. Then subtract. Okay, subtract the both numbers. You have 100n equal to 26.262626. And I have n, which is the first one, the original number, which is 0.262626. Then we're going to subtract this. Okay, the reason is that we want to be able to get rid of the repeating part, because it is difficult to just subtracting them when you still have those there. So when you subtract, this will be 100 minus n minus 1n is what? 99n. And that is, if you subtract this part, you're going to have this will be 0.00, and then you get what? 26 point that. And then you divide both sides by 99. Okay, which will give us what? 26 over what? 99. Now divide by it. Okay, you have 26. Can you simplify that? No. So that will be your what? That'll be your answer. Now, this example, notice that there's a digit 3 before the repeating part. Okay, so this is how we approach it. You let the rational number n equals to what? The original, you have a 2.309. Okay, now before you can subtract, the steps is that before you subtract, you have to multiply by something. Right, now I want to be able to write this number such that the repeatant comes right after the decimal what? Decimal number, just like in the example, the first example. Okay, so to do that, I just move this decimal to the right by multiplying by 10. So I get 10n multiplied both sides by n, 10. That would be 23.09 repeating. Okay, now again, the repeatant is what? The period is 2. The period is what? Is 2. So we multiply this equation here by another 100. So you get 100 by what? 10n. Now if you multiply the right hand side by 100, you get what? 2309 times 09.090909. Okay, and this gives us 100 times 10 is what? 1000n is equal to that 2309.090909. Then, so that's step 1. Step 2, then step 3 is what? Subtract. Subtract which number? This, whatever you have here, the one we were able to write so that the repeatant comes right after the decimal. So you have 1000, n is equal to 2309.0909. And then we have what? That is 10. So that is 10n. You're going to subtract, and this is 23.090909. Okay, so when we subtract, okay, this will be 1000 minus 10 is what? 990 n. And this side, if you subtract if you subtract 23 from 2209, you get 2286. Okay, then divide both sides by 990, and this side by what? 990. Okay, now if you simplify this, divide the top and bottom by 18. So this is divided by 18. So that gives me 127 divided by what? 55 in a simplified form. Okay, now finally Now look at this example. We have 2 digits before the repeatant. Okay, so 2.24, then 09, 09, 09, 09, 09. So same procedure. Step 1, you let your n be equal to the original number, which is 2.240909 repeating. Okay, since you have 2 numbers before, digits before the repeating part, you multiply by what? 100, not a 10. Because here it was 3, only 1 digit before the part that is repeating. You have 2 digits. If you had 3, you multiply first by 1,000. So you multiply by 100, 100n equal to 224.0090909. Now again, the period is 2, so that means we multiply by 100 again of that. So that is 224 and then 09.090909. Okay, so 100 times 100 is what? 10,000 n equal to 2,000 so 22,409.0909. Okay, then step 3, you subtract. Okay, so you get 10,000 n equal to 22,409.09. Okay, and then you just pick that, subtract the same thing, which is 100 what? You get 100 n. And this part is 224.0909. So that we can get rid of what? The repeating part. So 10,000 minus 100 is what? 9,900 n. And that is equal to 22,185 of that. Then divide both sides by 9900. 9900. Okay. And now see, I want you to note something. When you have 1, okay, if you have just 1 digit before the repeating decimal, okay, let's even go to the first example. See that we divided by what? The denominator is 199. Okay, when you have the repeatant comes right after the what? The decimal point. Okay, now if you have a digit before the repeating decimal, then it becomes 990. Now look at it, you get 990. Okay, you get 9900, and you have 900, 9,909, 9,900. Now look at the pattern, something here. Okay, all right, just compare the last two. Okay, you got 990. Okay, 990 is 10 because there's 1 digit that comes before the repeating part. Here there are 2 digits, so you get 99 and 00. So the number of zeros that we add to the denominator, okay, it will be 9, is equivalent to the number of digits that comes before the repeating what portion of the decimal. Okay, so if that means that if I gave you something like this, let me write it up here. If I say that 0. 0. Say 0.009, okay, then this is in a fraction form. There's a certain number, the denominator will be what? Will be just 99. Okay, because there is a number, the denominator we can figure it out, but the denominator will be what? Will be 99 because there is no decimal before the repeating decimal part of that. Okay, very good. Now, it's a find a rational number ordering of what? Repeating decimals that comes between this. So you have 0.35, okay, which is what? 0.35, 35, 35, And then the other number is 0.351. So this 0.351, 351, 351. I just want to write it, find a rational number in the decimal form between these two. There are uncountable number. There are infinite number of them. Infinite number of decimals that we can write. But one of them, okay, if I compare this, like we're looking at the place values, okay, I have 3.5 and 3.5. Then that changes. This will be 3 and then what? And 1. So between 3 and 1, I can have what? 2 there. So one of such rational number will be what? 0.352. It comes between these two. Of course, this one is smaller than the first one. Okay, so we can have this decimal right there. Okay, or we can have 0.3521. Okay, 221. This is a rational number in that form that can come between what? Between this. Or you can have 0.351, 352, 352, 352, which comes between these two. Okay, this also can be, and that also can be another example. All right, so with that brings us to the end of this section. Repeating decimals, repeatant, and then the period, writing a repeating decimal as a rational number in the form a over b. Okay, and then ordering of what rational numbers by comparing the place values. All right, so that is it, and I will see you next week.